Rika to share the screen.
Okay.
We can see your slides very well.
Wonderful. And if I press next, you can see the change in the slides, right? Fantastic.
Yeah.
Okay. So thank you very much for inviting me for this short talk. And I will be talking today about the challenges and opportunities of differentiable simulation. So first, let's step back a bit of motivation here is that we all know that robots are precise enough to assemble cars. They are resilient enough to drive on Mars. We've all heard of Mars rovers, and recently NASA engineers even made them fly on Mars. Yet, surprisingly, fully autonomous robots taking care of household chores and other routines, such as tending to crops, are far from being ubiquitous. So what is the challenge here in these unstructured environments that seem so easy to us humans? Well, robots need to learn to handle a variety of objects, for example, including adapting to new shapes of rigid objects, figuring out how to deal with highly deformable objects such as wires, sheets, and clothing, and also handling fluids and granular matter. And they also need to quickly incorporate environment feedback to adapt to variations in the physical properties of the objects. So we can guess that simulators can bring very useful priors, but simulators themselves actually need to be adapted to reality before they are useful. And so this is one of the use cases that is quite reliably beneficial when it comes to considering differentiable simulation. So here, the promise of differentiable simulation is that we will have a function f. So this is our simulator. But now this is not just a black box program with code. We can actually structure it in such a way that we can directly propagate the gradients through this program from the kind of output all the way back to the physical parameters of the simulator. And so with that, we can, for example, take something that we observe in reality and adapt the physics parameters of the simulator directly. We can also adapt the trajectory of the robot, and we can also do some advanced things like, for example, changing the shape of the robots and tools. So first, I'll talk about this real to sim. How do we adapt to the physics parameters of the simulator? You would think that if I gave you a differentiable program, right, you just propagate the gradient back. But actually, it's not that simple because what happens is that you have optimization landscapes that are pretty rugged. And so just the direct gradient descent would not necessarily end up in a good spot. So what you can do is what we've introduced here recently is we have developed a method that is hybrid. It combines a global optimization with semi-local population sampling with gradient-based optimization. And so with that, you can handle these challenging rugged landscapes. And here on the right, I'm showing an inference example for inferring the patch stiffness of different patches of fabric and paper. All right, so with that, we can also actually go further. So if we have a physics simulator, let's say, that is mesh-based, one question is, how do you propagate the real observations, such as point clouds? How do you propagate information from that? And for this, we recently developed a method that we call DiffCloud, which uses a differentiable point cloud sampling in order to incorporate a point cloud-based loss, like, for example, a chamfer distance loss. And with that, again, you can infer the parameters, the physics parameters of the objects, but now you are not forced to, let's say, somehow indicate the key points on the object. There's no processing that is necessary. You just have a depth camera and you directly read off the point clouds and propagate the loss like that. And we have shown that actually there are more than an order of magnitude improvements in terms of the training time, where here it's just direct optimization time, as compared to the non-differentiable version of trying to adapt the simulators in a more black box way. All right, so we can do real to sim, but as I mentioned, we can also do direct trajectory optimization. So for this, in our recent work, we built a suite of environments that have some challenging scenarios with rigid objects, with deformables, and with fluids, and also with plastic deformation. And with this, we have analyzed the optimization landscapes. They also look a bit challenging, but again, we gave them to the Bayesian optimization with this hybrid global and semi-local and local optimization. And on the left there, you can see an example of an optimized trajectory, which successfully completes the task, even though the optimization landscape is quite challenging. All right, this also works on plastic deformation, but here the challenges are actually different. The landscapes are pretty smooth, but there are plateaus that would prevent the gradient descent from, actually descending, right? So it would get stuck on a plateau. For this, this combination of the global and local optimization is also useful. Now, there's still some challenges remaining, and one of them is basically how to handle rigid context. So even when you have a number of rigid contexts that is not very large, you can get into the optimization landscapes that look like this, which are pretty challenging. And so this is still pretty much a bit of an open problem in the differentiable simulation community. All right, so now stepping back, what else can we do with this? I mentioned that we can optimize the shape of the robot or the tools, and this is morphology optimization, and I will talk a bit about that now. So in 2021, a team from MIT introduced a work called DiffHand, where they were actually changing the shape of each component of the robot hand, or rather here it's an arm. And they were using something called cage-based deformation, which is a technique or a family of techniques that has been introduced in the graphics community and has been used in the graphics community for a while. And it allows you to basically pull on one piece, let's say, so on one part of the mesh, and let the rest of the mesh deform nicely, smoothly with good properties. So with this, we have looked at the optimization landscapes that some of these tasks kind of yield. And we've noticed that when you are actually operating in free space, so like, for example, you're trying to reach a certain target, the optimization landscape is actually not that challenging. But the challenges, they begin when you're actually considering context. So even if you have the formables, like here, for example, we envision the task of having to come up with the shape of the tool such that when you wind a rope over that tool, the rope doesn't slip, right? So you can imagine if you just start with just a regular block, right, and you try to wind something on it, it will slip right away. And so a smart optimization algorithm might be able to find like this nicely hourglass-shaped result. All right, so we call this the winding task, and basically we look then at the optimization landscape of that kind of task. And as you can imagine, since there are contexts here, even though they're not rigid necessarily, there's still challenges here in the optimization. All right, so here we're actually going to insist on just staying within the differentiable land and do everything end to end. But we will observe that we need additional kind of power for this because the landscape is pretty challenging. And here, this is another work that we've recently presented last year, which shows that we can learn sequentially. So basically, we can sample different task variations, and with that, we can use continual learning insights in order to create learning for a robust morphology so that it is robust to task variations. All right, so how do we do this? So first, our first observation is we need to reduce the dimensionality a bit. So on every iteration, because now we're learning sequentially, we can subsample a set of, let's say, pieces of the cage that we're going to actually be adapting, and then just adapt that part. So that reduces the dimensionality and simplifies every, the landscape a bit on every iteration. And then the main insight here is that we actually want to employ continual learning. So we've explored kind of how to extend a few different versions of continual learning works. And we came up with a way to basically combine the task loss with a distillation loss. And here the distillation loss is basically aiming to retain the knowledge from what we have learned so far or where we have arrived at when optimizing on other task variations. And so with that, we have tested what we've got on the flip task, which is the task that was introduced by the previous work. And we've got quite a strong improvement there. And basically, the previous work here, the task is to flip the cube. But the challenge is that, original work just wanted to flip the cube from a given position, but we're actually allowing to vary both position and orientation. And then you can see that the previous work is kind of not enough to flip the cube in all cases, whereas we're able to handle these variations. Then we looked at another task, the pushing task. So here the idea is we want to introduce, so this is a tool optimization now, not optimizing the shape of the robot, but optimizing the shape of the tool. And we want to come up with the tool that will be able to help us push in such a way that objects that are even easily, that can easily roll away, they still stay within the this kind of hugging area of the tool. And here I'm visualizing the result with the optimal tool that we have found. And finally, I already mentioned the winding task. And so this is how the result looks like for the winding. All right, so I've looked now at how to optimize, how to use differentiable simulation to optimize physics parameters, how to get the policy parameters, and how to optimize morphology. And what I've mentioned so far very briefly is that we can use hybrid search to combine global and local optimization. We can directly optimize from point clouds. And we've also recently described how to use continual learning in order to optimize morphology in a robust way. Right. Thank you.
Amazing. Thank you so much, Rika, for your great talk. Very interesting. And now I think we have